Okay, so last class we looked at the common source amplifier, right? We looked at the output impedance, gain, and so on. So one other factor which we didn't discuss. So we looked at the gain was GM1 over GDS1 for this transistor, but that is the magnitude. What about the phase? Right? This has a negative sign, right? So if your input is at a certain phase, output is 180 degrees out of phase with the input. Same thing for all of these. Okay? But the amplifiers we are going to look at in class today, I think you already know the other two kinds, the common drain and the common source. The common drain and the common gate. Those two have positive gains. Okay, so let's start off looking at the common gate. And so today we look at the common gate and then the common drain, and then we'll look at some modifications of the common source, okay, to improve certain qualities. So let's call this the bias. Okay, so this is your common gate amplifier with a resistive load. This is your VI, right? So let's assume that a current IT flows out of VI. Okay. So the reason we'll call it IT is we're going to assume it's a test voltage, test current, and so let's call this VT. And first of all, we want to find out Rn, we want to find out R out, and you want to find out gain, these three parameters. Okay, so we can calculate in there's no specific order. R out is probably the simplest, right? So what is R out? What is the output impedance of the common gate? Sorry? GD by? GD plus? So, right? 1 over GD plus GDS1. Is that correct? It's fairly straightforward, right? When you're trying to find the output impedance, you turn off the input source. So you short the input source. Then it's just RD in parallel with RDS of the transistor, right? So next, let's try to find out the voltage gain. So to do that, we'll do a KCL, write the KCL equation at the drain, which is this. Okay. So what is this current? The current through GD. What is that current? Right? It's IT. If you do it the other way, it's minus IT. Right? remember that IT is also, so that IT is equal to sum of these three currents. Okay, but that is also equal to V0 times GD, right? So we'll first write that down and then go on to write the KCL. We'll change the order of these two. Okay. So GD times V0 plus, what is VGS? Gate is grounded, VT, okay, minus VT, right, plus again GMBS times minus VT plus GDS times V0 minus VT, right? Equals 0. Is that clear? Okay, so that's GD times V0. So we'll group V0 on one side, VI on VT on the other side. Correct? Okay, so this is the accurate expression for the gain, GM plus GMPS plus GDS over GD plus GDS. Next, let's try to find out, and of course, you can approximate this in many cases, right? So we know that GM is much larger than GMBS, which is much larger than GDS, and right, GD is much larger than GDS again. So quite often you can approximate it to GM over GD or GMRD. You could have seen that, right? Next, if you want to calculate the input resistance, right? You know that your IT is nothing but GD times V0, which is GD times AV times VT, right? Sorry. This is the expression for the input resistance, right? Now you could say that you remember, I think yesterday or day before somebody was saying that you were saying that the input impedance of a common gate is 1 over GM. I think you would have studied that in the previous course, right? Has everyone studied that in the previous course? Input impedance at the source, right? But what this shows, this is the accurate expression for that. What this shows is that it's actually a function of the drain impedance also, okay? Obviously, if you left your drain open, if RD was infinite, input impedance would also be infinite. It's not always 1 over GM, okay? and you will see circuits later in this course where the output impedance is actually of the order of GDS or even much larger. Okay, so don't always assume that the input impedance at the source of a common gate is just 1 over GM. Okay, it depends on the impedance at the drain. Of course, you can simplify this a little bit further, so that you can do. So this happens to be right. So of course, if GDS is much smaller compared to GD, this is true. What? Oh, did I say R out? Sorry. Okay. Again, this thing is here. Okay. So just remember this. Remember that the input impedance is also a function of the drain impedance. Okay. Next, we'll look at the common drain. So let's write it like this. Let's write it in a slightly different way. So let's say you have a very large capacitor at the source, decoupling the output from your actual source. So if you draw the signal picture, the capacitance is a short. You have RL here. This is V out. So we'll write, since we like to use conductances, I like to use conductances, so I'll use GL. Okay. Use your source. This is your bulk. Okay. Let's just quickly write down the expressions for VGS. So VGS is nothing but VI minus VO. Okay, this helps a lot. If you just write down simple expressions and then substitute them later, it's a lot easier. You won't make any mistakes. Okay. Let's do a KCL at the source. Actually, GM into VI minus VO plus okay. Right? Right? So this is the expression for the gain of the common drain. Okay, so it's GM over GM plus GMBS plus GDS plus GL. And again, quite often you'll find that GM is much larger than GMBS, much larger than GDS. You can make, rational approximations. You can show that this is approximately equal to 1. Okay, it will be slightly less than 1. And as far as the output impedance goes, you can show that the output impedance is 1 over GM plus GMBS plus GDS plus GL. Okay, or you can approximate it to 1 over GM in parallel with RL. Okay, so we are done with the simple circuits, right? This actually, I assume that most of these you've already seen before, except for the GMBS and so on, right? Except for those factors, you would already seen all of these circuits. So let's look at some other circuits. For example, the next circuit we're going to see. Have you looked at this circuit, a degenerated common source? No, not yet. Okay. Okay, so you take a common source and add a resistor at the source, between source and ground. Okay, this is called a source degeneration. Okay, so an easy way, okay, so the reason we are splitting it up this way is you need to know all these output impedances, input impedances, because this will help a lot. So later when we start analyzing op amps, poles and so on, you probably should know all of these. For example, what is the output impedance of this degenerated circuit? What is the input impedance of a common gate with something at the drain and so on? Okay, at that time I won't be stopping to rederive all of these things. Okay, so just make sure you understand these very well. Okay, so let's say you want to find out the gain of this. Okay, one way to do this is to split it up into two components. Remember, I talked about voltages getting converted to currents, getting multiplied by impedance to convert to voltage. So that is a good way to analyze even this circuit. Okay, so you can split it up into an effective transconductance and the output impedance. Okay, so the product of those two is going to give you the gain. Okay, so in other words, you're going to find out the effective transconductance of this circuit. And then you can multiply it by you're going to find out the output impedance, multiply the two, that gives you the gain. Okay, so one easy way to do this is to short circuit the output and find out the current which is being drawn. Okay, that will give you the transconductance, right? So let's quickly draw the small signal picture. Okay, so I'm going to call this VS, GMBS VS. Oh, okay. Okay, again let's write down what VGS, what VBS is and so on. Trying to find out the drain current here, right? Again, you can write this current is the same as ID. This is GS. Okay. Right? Okay. Next, we'll do a KCL at the source. Okay. What is VGS? VI minus VS. Okay. And VS is nothing but ID over GS. Because remember, we are trying to bring it to the two parameters which you are interested in. Right? What are we interested in here? This is what we are interested in, right? The effective transconductance is nothing but ID over VI, right? That's the reason why we are bringing everything in terms of ID and VI. Okay. So this plus, what is VBS? Minus VS, which is minus ID over GS. Is that clear to everyone? Right? You just group the two terms on either side. So the transconductance is nothing but ID over VI. Okay? We'll just write 1 over GS as RS, right? It's slightly easier to visualize, that's all. Okay? And if you assume that GM is larger, if you want to make some engineering approximations, GM is larger than GMBS, larger than GDS, then the effective transconductance is nothing but GM over 1 plus GMRS. Have you seen this before in any circuit? You have. Right? You would have seen it in that kind of circuit. Yeah. Okay. The reason is, if you take the circuit, okay. If you apply this approximation, right? Right? If your GM is large enough, effective GM is nothing but 1 over RS, right? You would have seen, so this is actually quite useful because what is effectively happening is your GM of your transistor is actually a function of a lot of parameters, right? It's a function of the current, it's a function of the voltages, it's a function of the process, right? Whereas if you add this resistance, it is becoming closer and closer to an ideal, right? Ideal inverse resistor, right? In other words, the transconductance is now proportional only to the inverse of the resistance. It's independent of voltage, independent of current, independent of a lot of parameters. Okay? So this is called, so basically adding the resistor there is called source degeneration, and effectively what you see is it reduces the transconductance, right? Because inherently you are putting this parameter, GM is much larger than 1 over Rs, and if your new transconductance is 1 over Rs, it is much smaller than the GM by default, right? By definition. So in other words, you are linearizing the transconductance of the circuit, but you are giving up the actual transconductance value. You are getting a much smaller value. Okay? So there are a lot of ways to look at this circuit. So one of the ways, so if we just take this circuit, right? So another way to look at it is, you can look at the signal from going from here to here as some kind of source follower, right? So in other words, you could say Vi by Vs is 1, approximately 1. Okay? What is ID? Right? This is another way of looking at it. Okay? Okay? So what next? We found out the gain of the circuit. So next step, what else have we been looking at? Obviously input impedance here is infinite, so no need to calculate that. What about the output impedance? Have you ever calculated the output impedance of such a circuit? No, not yet. Oh, you have. Okay, what is it? If you say yes, you have to tell me what it is. Okay. What is it? This is what you said? No 1 over GM. So it's just RD parallel with RS. Is that right? Does that look right to everyone? Okay, then what is it? You've seen this before, right? Okay, what is it? GM squared? Okay, I'm hearing a lot of interesting numbers here, whatever, expressions. Okay, anyways, let's calculate it out. It doesn't take a long time. We'll just spend a few minutes calculating it, okay? So, of course, all of these are wrong. Okay, I can tell you it's not directly RD parallel RS, it's not GM squared, okay? So, let's quickly calculate it, right? Okay, so we're going to apply a test source, ground the input, apply a test source to the drain, right? Find out the current taken by the taken by the circuit. VT over IT will give you the output impedance, right? Okay. So first of all, VGS is minus VS, okay, which is minus IT times RS. Or let's write it in terms of GDS. I don't, okay, GS, because let's just follow one convention. Okay. Right? Both of them are minus VS, which is minus IT over GS. Okay, now we'll write KCL. At either drain or source, doesn't matter. IT equals GM times minus IT over GS. Okay. GMBS times minus IT over GS plus GDS times basically VT minus VS, which is VT minus, sorry, is that right? Yeah. Okay. Is that right? Correct? Right? It's GM plus GMBS plus GDS plus GS over GS times GDS. So let's write this in terms of the RDS. Okay, now we want to start looking at the impedances. So we'll start making some, again we'll assume GM is large enough, can neglect the other terms. Oh, sorry. Okay. Oh, sorry. Why do I have this one here? So it's RDS times. So you're neglecting these guys. 1 over GDS is RDS. 1 over GS is RS. Okay. And let's also again, I should have written this differently right at the beginning. Let's write it in this way. Right? What is GM-RDS? That's the intrinsic gain of the MOSFET. Right? The intrinsic gain of a MOSFET is GM-RDS. Okay. You remember this expression? GM RDS times RS? You do. At least some of you do. Okay. So, anyways. So, this is the overall output impedance. So, the output impedance of a normal transistor is just RDS. Right? So, now this is actually larger. It's GM RS times RDS. Right? That is one way to look at it. The other way is the next structure we're going to look at is what happens if you replace this resistance by another transistor. Okay? And that's called, yes? Yeah? To the circuit or to the diagram? Here. This one, the small signal model or the, okay. Okay. Sorry. You're right, I have neglected that because I have assumed, okay, I should have mentioned it because, okay. So it's actually, you're right. So, let me call this, okay, which is approximately equal to R01. Okay, because GD is the resistance which is probably in, okay, so if you start looking at numbers, right? If these numbers are, let's say, in kilo ohms, so if GD, these resistances, GD, GS, RD, RS are all in kilo ohms, and if you have a decent amount of gain here, right, your actual output impedance, GM RDS times RS, is going to be much larger than RD, right? Sorry? It's parallel R01, right? This is VO. Okay, what did we find? Let's draw it again. Right? We found out the output impedance here, which is R01. Correct? What is the overall output impedance? It's R01 parallel RD, right? So what's the trouble? Oh, I see what you're saying. Yeah, you're right. Sorry. My mistake. You're right. Sorry. Yeah, I meant RD. Sorry. R01 is much larger than RD, so it's RD in this case. Okay. But what we are going to use is, okay, let's go to this diagram. It's a little bit better. We are going to use this portion of the circuit. Okay. So RD was just a representative load resistor. We are going to use the bottom portion of the circuit to create what is called a cascode. Okay. So let's make things easier. Let's use an ideal current source. Okay. Let's use an ideal current source. Okay. What is the output impedance of the circuit? Right? Look at this expression. It's GM RDS times the impedance at the source. right? So the output impedance of this is GM2 RDS2 times the impedance at the source. Is that clear to everyone? Which is RDS1. Effective transconductance is just GM1, right? What is the gain of the circuit? Correct? We'll write it slightly differently. So what is this? GM1 RDS1 times GM2 RDS2, right? GM1 RDS1 is the self gain of the first MOSFET. GM2 RDS2 is the intrinsic gain of the second MOSFET, right? So in other words, this is equal to the gain you would get if you ended up cascading two of these, two simple common source amplifiers, right? If you just have a common source amplifier with a current source, the gain of that is GMRDS, right? So this single stage actually gives you the same gain as you would get from two stages. Yes? Sorry, the answer changes if? Of course. Definitely it will. Of course. Yes, it's a cascode. So which answer would change? Okay, actually let's look at that. What would happen? This was VI. This was VB. Right? Okay. What is the output impedance here? Same. What is the GM? What is the new GM? We just looked at that. Right? It's clear that the answer is different. Okay? What are the advantages? Of course, high gain in one stage. What are the other advantages? Since it's happening in a single stage, it's quite possible you could expect that the stability would be quite good. You have studied stability, right? The fact that if you have multiple stages, you could have problems with stability. I'm sure you have studied that. Anyway, we'll come back to this, the stability of the cascode. But there is reason to believe that the stability is better than two common source stages. What else? Power efficiency. So if you had two common sources, the total current you will be consuming to get this gain would be I0 in each, okay, which would be 2 I0. In this case, you're getting the same gain with half the current, okay. What are the disadvantages? What do you think are the disadvantages? What overdrive voltage? Okay, yeah, you're kind of on the right track, but that's not the way I would put it. So one of the things is because you're stacking, you end up stacking two of these transistors. In a real case, if you're using this for an amplifier, you require a certain swing at the output, right? What is the lowest this output voltage can go such that these two transistors are in saturation? So you can bias it such that this will just go into saturation VD sat, and this will also just go into saturation VD sat. So it's 2 VD sat, right? So if VD sat is, let's say, 100 millivolts, output can swing only down to 200 millivolts. Whereas if you had two common sources cascaded, the output can of the overall amplifier can actually swing down all the way to 100 millivolts. Okay? This is often called headroom, voltage headroom. Okay? And this is actually becoming a problem as you look at modern processors, because the power supplies are becoming smaller. Right now the power supply for a new, the latest process is probably a volt or even less. Okay? So you can't afford to have, another 100 millivolts. That's 10% of your overall swing. Okay? You can also look at this intuitively. So let's take a cascode. So let's say you're trying to, so if you want to find out the output impedance, let's say you try to pump in a current delta I into the circuit. Okay? What happens to this current? It flows through 2 and 1. It creates a delta V here, which is delta I times RDS1, right? What happens to the gate source voltage of M2? So now this voltage tends to increase, right? So that's basically reducing the headroom, reducing the overdrive, the VGS for M2, right? So in other words, if that reduces, that tends to oppose the change in delta I, change caused by delta I. Is that clear to everyone? So you can think of it as some kind of negative feedback. Okay? So that itself shows that the circuit should actually have a very large output impedance, because you're trying to send in a delta I, but the circuit is actually opposing it. Okay? That is the definition of a very large output impedance. Okay? Okay? Now the question is, so now you have almost doubled the gain from a single stage. Can you do better? You just have, let's say, one single stage. Can you do better than, what is the gain we got? Minus of GM RDS1 times GM RDS2. GM1 RDS1, GM2 RDS2. Can you do better? Yes. Okay. So if you have a very large output impedance, right, for any circuit, what that means is if you try to inject some current, that circuit actually opposes that change in current. Okay, if you take a current source which has infinite output impedance, you try to inject some current, you can't do it, right? So let's say you try to inject some current into the circuit. Let's say the current is delta I. The delta I multiplied by the output impedance of this first transistor gives you a delta V, which is delta I times RDS1. Correct? What happens to the VGS of this? It tends to reduce. Right? Earlier it was VB minus whatever voltage was there. Now it's that same thing minus delta I times RDS1, because this thing is starting to increase. What happens when this VGS reduces? The current through this transistor tends to reduce. Okay? So you can think of it as some kind of negative feedback. Okay, there is some implicit negative feedback going on in there. Okay, it's not explicit like you're used to, which is, you take, sense something and then send it back. here you are sensing something. You are sensing this change in current and applying it as a gate source voltage across this transistor, which is opposing that change. Okay? Okay, so let's stop here. I think it's already, yeah, we only have, we're already over time. So let's stop here. So tomorrow we'll see one more way of getting even more gain, okay, from a single stage. That's called gain boosting. We'll look at that tomorrow morning. Not tomorrow, Tuesday. Okay?